for the next speaker from Royce. And no idea what it's going to be about, but presenting something related to machine learning, I see, from Rolls-Royce. Please give it up for Jussi Poikonen.
Thank you, and good evening. I'll introduce myself. Jussi from Royce. I'm an AI development lead. Usually I go around talking about the business aspects of what we're doing, how is AI used in our business of making autonomous ocean-going vessels. Now I heard that there would be software developers present, so I thought, yes, this is my chance to talk about something practical and cool. So I want to talk about training object detection models, which are a very important machine learning component in our systems. So I hope that you are software developers. Who is a software developer or something like that? Okay, cool, excellent. And how many of you have trained machine learning models? Okay, not so many. So I hope the rest are interested in the topic, otherwise you will be bored for half an hour. Object detection, well, if we start a little bit with the business, what we use it for is in these situational awareness systems to be able to track objects like other ships. We have to be able to first detect where they are. So we would, for example, detect a fishing vessel in the camera and start measuring its location with a radar or LiDAR, something like that. That's the basic concept. And this is already a kind of sensor fusion that gives you a picture of the surroundings. There are very good models for doing this kind of object detection. Nowadays, neural network architectures are really state of the art. You can get close to human performance with these kind of models. And I'd like to talk about how you can train this kind of model with kind of very accessible tools, stuff that you can buy with not so much money from the shop and use material from around the house for, if you like, for training a model. You could train a model for detecting what is in your refrigerator and giving you the information. Of course, there's no light there, that's the problem, but in principle, install a light there. So what you need to build a state-of-the-art object detector. This is the model that we are, for example, using in our actual systems. So in principle, it's really simple. You need a camera to produce images. You need some kind of computer. For training an object detection model, it doesn't even have to be a very good computer. You can use cloud environments, Google, Amazon, Azure, whatever. And basically, I'm showing you some computations on how to produce training data for an object detector on this crummy laptop. It's the actual training of a neural network and running a neural network, which demands more hardware, and that's where you would need a GPU if you want to do this in any reasonable time. Even that's not necessary. If you are very patient, you can use whatever. So, yeah, you need a computer which has some interface for the camera, some image processing libraries, and some machine learning framework, and some kind of a model applied to that framework, and something to run the neural network on. An example that I have used for an actual demonstration, which you will see in the end of this presentation, what that is in practice about, but this is a very good setup if you want to do an object detection model which will run in real time with very good accuracy. So I used a GoPro. Now, the challenge is how you connect a GoPro to any computer. It is, by nature, HDMI is a very kind of good way of connecting it, but usually computers don't take in HDMI. So I use the Blackmagic Design Intensity Pro 4K. We can Oh my God. Just a second. I do have the internet with me. I hope. Because I want to show you some online links perhaps. We'll have to skip those if I don't get it working. Let's find Wi-Fi. Yes. Okay. No, don't worry. It will come back. Okay? Yes. So, this is the Blackmagic device is a frame grabber. Looks like this. You put it in your computer, plug in the HDMI input, and you have a pretty nice SDK which allows you to grab images in many formats. I think this does up to 4K resolution. And you have to do a little bit of tweaking maybe to get the signals to a form that you can use. So we did a little bit of coding, it's in C++, to transform the input image into kind of an array resembling a Python NumPy array. Let's see if I can get back to the presentation. Okay. Then you need something for image processing. I use OpenCV with Python, typically. As I said, you have to first use the frame grabber SDK to get some signals there. Then you need to give training information to your neural network, machine learning model. And I'll talk about this in some more detail later. TensorFlow uses something called TensorFlow or TF records. Now there are many machine learning frameworks. TensorFlow is from Google. It's an open source architecture which is quite popular and provides very flexible possibilities and ready-made models. I would suggest using that. And then you would probably want to have some kind of GPU. I used an NVIDIA GTX 1080 Ti, which is very good. Basically, it's for gaming, but the performance is let's say, sufficient for doing this kind of stuff. Now, of course, you have other options. You could just use a USB webcam with the OS drivers. Pick any machine learning framework. There's in the TensorFlow detection model Zoo many options for these different models. I can show you some examples, perhaps. This detection model Zoo is very handy in that it tells you an estimate of the computational load of these models. So I use this faster RCNN ResNet 101, which is a quite heavy network. You can do a lot faster if you use, for example, the SSD. And there's also YOLO, you only look once, which is a really popular framework. It is entirely in C++, it's really fast, but it is proprietary to its developer. I mean, in a business context, I would not use it, but perhaps if you just want to make a detector model which is fast, you might consider using this. You can run stuff on CPU if you make a smaller model, and also you can use other accelerators with, for example, OpenCL. Okay, this is what you need to kind of generally run this kind of stuff. Now, for doing for generating training data, in the kind of cases that we do for our ships, it's a big challenge. We have to get a lot of different examples of ships in various conditions, all kinds of ships, and kind of either we measure all of those by ourselves or try to gather them from some public sources or whatever. It's a huge task. But you can do the same thing with whatever, take a beer can and produce a very good model for detecting that. And you will kind of see the same effects that you need to do with real-world data from whatever business application that you are working with. So I think this is a really good exercise to do this kind of sandbox for object detection. Because you have to make the data yourself so that you get a good model and you learn how to make a good model. What you need for this kind of approach is chroma keying materials. I bought some green cloth from Eurokangas here in Turku. It cost like €5. That's the only thing you need. Now, to try this, what I'm going to talk about into the marine scenario, for Daphne the duck went missing on March 2018. So let's figure out a way to make a detector that would find Daphne the duck from camera images. Okay. I'll talk about basically an image processing pipeline for preparing data for training an object detection model. For that, we use the green fabric, put the object you want to train on top of that, and take first a couple of images to prepare the kind of processing pipeline for making the training examples. These are the examples I'll be talking about. So if we look at the actual Python code that you can use for this. Let's go through this. This is, I guess, boring for some, but interesting for others. I'll try to be not tedious about this. So you can see the libraries. I've been using the kind of normal Python libraries, NumPy, OpenCV, nothing special. So let's look at the, oh, sorry. You have to run all of these. Are you familiar with Python? Who uses Python? Okay. Jupyter Notebooks? Yeah? Okay, cool. So Jupyter Notebooks are a way of interactively running Python code. So if we look at the training examples we have 13 JPEGs. Now let's plot a random example. We can choose the duck image we want to process. This is a boring one. Yeah. Can we? Okay, maybe this one. Yeah. So here we have a duck on a green background. We want to extract this duck image and put it on different backgrounds to generate a very large number of training examples. Now, this is now very practical. How do you extract the duck from here? Well, one problem you can see is that the image is too large for our neural network. It's 3,000 by 4,000 pixels. That's too big. And the borders are not clean, so there's stuff around here which is hard to remove. So let's crop the image. Okay, this is better. Now we want to extract the duck out of this. So what you do in chroma keying is find anything that is not the background, that is not a shade of green. So we do some color filtering. Basically, you can do this with an OpenCV in-range function you define for each of the color channels, blue, green, and red, the minimum and maximum. This takes a little bit of tweaking, but you can find pretty easily the region where you have something which is not green. Okay? Now we have kind of the duck separated, but this is noisy. You have this kind of dot noise here. And you can clean this up with morphology. Maybe I'll not go into that so much, but it's a kind of local region processing which you can use, for example, to remove noise out of images. If we apply a morphological opening operation, let's see what we get. This is pretty close to the shape of the duck. Now you can tweak this a little bit. You can change, for example, the kernel, which is the size of the neighborhood for the morphology. Yeah, that looks kind of like a duck. And now we can use this mask image obtained from the morphology to pick out the duck part of the original picture. So we just do an AND operation between this mask image and the original image and see what we get. Okay, that's pretty much just the duck, right? Which is good. We can now cut this part of the image and put it on any other image. But for training an object detector, we also need a bounding box, because that's what an object detector produces, and the training data needs to be that also. So we need a box around this. We need to know where this is in the picture. And you can do that with an OpenCV function called connected components. So it tries to find pixel regions in an image which are connected to each other. If we apply that to this mask image, it will probably find the head here and the body here. Let's see. Okay, it finds 3 regions. The first one is the whole background image, and then 2 examples. You can see the size is this one here. So I picked the largest component out of this image, and then I can plot that here. Okay, that's the body. Now this is not the whole duck. This is a little bit failed example maybe. Actually, I can even improve it, I guess, if I change this kernel back here. So this is kind of like a feedback process. Let's try. Okay, now the head is attached to the body, which is good. Now we should have less components, maybe. Let's see. Oh yes, so we get the whole duck. It's very good. Now we have the bounding box and we have the duck example. Now we want to put the duck on a better background. So let's load something from the internet. I have a URL which I have previously picked to be suitable for this application. This is like a duck pond. So now we just cut the duck image out of the black background using the mask that we have. Use the mask to kind of remove this and combine them. And now we have a really good training example for training a duck detector. We also have the bounding box and information. Now if you do this kind of training, remember, do not add the bounding boxes to these final images. That will confuse your detector, because in real life you don't have boxes around the stuff it's looking for. It will learn to look for the boxes, I'm pretty sure. Now this is just one image. You need, I would say, let's say 10,000 to 100,000 examples to train a good detector. The easiest way to do this is probably to use video files as the input. So you can shoot a video with the duck for a while and shoot a video with a lot of different backgrounds and then do the same processing with those. And you can also combine multiple types of objects. If you go with the refrigerator example, you can have cartons of milk and cream and even beer, if you like. I can show you an example of this video processing. I won't go through this in any detail, but this is the actual code that I used. So I have a function which is just the filtering. I have something for plotting the bounding boxes. I have transformation operations. This is really important. You need to make many kinds of examples of the target objects. You need to translate them around the image. You need to change their sizes, maybe rotate them a little bit. You want to have all kinds of examples that you would ever see of this duck. So what I do is I have coefficients, random coefficients for scaling, value multiplication, rotation, random mirroring, all kinds of stuff defined here. You can figure out whatever you want to do with it. I defined some folders with the background images, some movies which contain ducks on a green background. And then I just run this for the video. Let's see if it works. Okay, now it is making a lot of training pictures. And it's really important to have the background images be something that you would actually be seeing in your application. We were making this demonstration for the office, so I went around the office with a GoPro, recorded stuff, people there. Especially people's hands are important because you will be seeing them. If this demo is about showing stuff to the detector, and it will think your hand is Let's see, if it has never seen hands, then it will probably think your hand is a duck. But let's show hands in the background, and we know that those are separate from the duck if we have enough examples. Okay. That was the training. It's quite straightforward and produces very good results. This is probably the best duck detector you will see all week. So I can show you the kind of source videos that I used. Maybe if this runs. No, these used to be videos. So I did the same thing with just kind of dangling the duck with a piece of string. And then we do all this stuff that I talked about. And the annotations are in CSV format. Images are whatever. Now to set up the training for the actual network, if you use TensorFlow, like I did, you need to serialize the training data to TF records. Here's a link, I won't go there, but you have the instructions, you can just follow those. And then you just run a script for training this specific network. Everything is kind of given to you. It's only generating the training data which is difficult, and this applies also in the business context. The training data is the gold, as they say, it's the new oil. You can do this to make your own oil. So if we look at this, now this is a hard thing to grasp what's happening here. I have an iPhone in my hand, which I'm using to film a monitor, and in my other hand I have the GoPro, which is kind of looking at the duck. Okay, so this is how the detector works now. And I did this teaching exactly as I showed you. It is very good with the duck. Is there somebody from Vincit here? I'm sorry, your duck is not recognized as a duck here. This discriminates against your duck because it thinks that the yellow duck is only a duck. And this is actually, I trained this model a little bit less, and it thought that the Vincit duck was also a duck, but then I trained it a little bit more, so it specialized more into my yellow duck, and now it's very like, yeah, only the yellow duck is an actual duck for this guy. And to be fair, I have some additional processing after the detector to smooth the detection, so this has a tracker which improves the kind of smoothness here, but the detector itself is also very good. And okay, this is not just for finding ducks in reality, so we have a experience space in our office where we can demonstrate these kind of detection functionalities. So here, I'm sorry, this is a vertical video, that's silly. But we have different types of ships, and we can demonstrate to customers or whoever that, okay, we can do this kind of detection. But the duck is, I left the duck there because it's fun. But the actual targets for these kind of different ships, so we have a bulker, a tug, and a passenger vessel. And this is taught with the same pipeline, so you just have to specify what the object is that you have in the images, and you can combine these and whatever.
One quick question.
Yeah.
If the duck would be yellow and the same colors, but maybe the shape would be a little bit different, would it still recognize, or do you have to teach it per?
Yeah, that's kind of a generalization versus specialization. So it kind of depends on what you want. If you wanted to separate these, then you can generate the training data set so that you can find the exact specific duck that you want, but that can be considered overfitting. So you have to kind of figure out when to stop learning. So if you teach a little bit less, then it will be more generic probably in what it thinks is a given type of object, but then you may get more false positives also. So this is a kind of the actual training process is you just have to play around a little bit and look at how it works now, and then maybe teach a little bit more, change the training set, and it's this kind of iteration of learning.
Because I was thinking if you have cargo vessels, they might be 250 long or 300 meters long. They might have 2 or 3 or 4 stories of these containers on top and stuff like that. You know, the where you steer the ship from look a little bit different.
Yeah.
It's still a cargo ship.
Exactly.
So it's depending, of course, on what you...
But the important thing is to show enough examples of all the variations that are within one class. So for example, for the duck, why we rotate it, why we change the size and so on. So it is still a duck even though it has been turned around. So it's the same thing. If your cargo vessel is small or large or different shapes, you just have to show the examples.
If you notice that you've taught it too much, it becomes too specific. Is it possible to rewind, or do you have to start from scratch?
It's not easy to rewind with the same method as the teaching. You should save these checkpoints. And this TensorFlow, for example, saves some checkpoints, but it's a good idea maybe to do the training like maybe 50,000 examples and then save 50,000 more and so on. I used about 150,000 iterations to get these models, and that was pretty good results. But yeah, it's kind of there is no rules. There are guidelines for how you can do this well, but it's sometimes hard to know what's the best choice. Yeah.
About the training, it was a bit quick for me. So was it unsupervised completely, or there was labeling also? Or it was completely unsupervised?
This is fully supervised. So I can show you maybe the training data actually. Can you see this? So what we were producing here were actually the data for supervised training. So we have the pictures that I showed you, and then for each picture I have a CSV which tells you that yes, here we have a duck and it is at this coordinates. Yeah. So that was what was part of the pipeline, was finding the connected components, gives you this box, and that's the supervised training part. Okay. I'm actually at the end of my presentation, so please ask questions if you like. I don't think I have anything more. Yeah. Any other questions?
Yeah.
Yep.
Hold on, I'll bring the microphone over. I think everyone in the front can hear well, but it won't carry to the back.
Yeah, how about the model? Are you also taking into account the moving pattern of objects, size of objects? Is that something that will be built on into these models as well?
The size of these objects?
Yeah, the moving pattern of, for example, a tug or a sailing vessel compared to a bulk carrier.
No, in these kind of models, these are fully frame-based. So it's just from individual images. And then for video, we use, you can use, for example, tracking. So when you find something, you can start tracking that in the video and try to kind of combine the detections and the tracking results to get a smoother result. And of course, there are models for doing video detection. So it's basically a three-dimensional convolutional neural network. So you take multiple frames into the model, and it tries to find certain kind of movement there. But this is fully frame-based.
Okay, thanks.
Yep.
So if one wants to experiment with this one, how much work is that approximately to make a small model like this?
How much work? This was basically the full setup. It will take you, okay, you have a computer, you need TensorFlow. If you build it from source, which is a good thing because it will work better on your computer, it may take 2 hours, it may take the whole day or the whole week, depending on how good instructions you find. It can be a little bit tedious sometimes. And then you install all the dependencies, that's like a few hours maybe. For the training, well, you could use this code that I have. Maybe we could even share it somehow. And that's pretty much all you need. So for generating a training data, the main effort is in then generating the source videos. So you get the fabric and put the objects there. So that will be like a couple of hours. Then the actual training, if you have, for example, a GTX 1080, then I think for me it was like 10, 12 hours to train some 150,000 iterations. So I guess you could do this in a couple of days, even in a day.
Yeah, I heard 1 day, so. Okay, but, well, okay, one more, because it's Andy.
How do you deal with like unintended bias when you're training these models? Like you're training on, say, European ships, and then, I don't know, a Chinese ship might look very different. How do you make sure you don't like exclude a class of things that you don't even realise is there?
That is difficult. I think you have to know what's in your data set, because the data set is the only thing that specifies the model, right? So you just have to be sure that you have a sufficient coverage of examples in the data. I don't see any shortcut there. Of course, then you test your model. I mean, if you know that something is dangerous, you don't want to see something be wrongly classified, then you just have to go and test. And preferably, when it goes wrong, you store those examples and take it back, label it again, and take it back to the training. And of course, in real life, we do this with real life data, and it's really hard to do this in an automatic way as I did here. So you have to use crowdsourcing basically. So that's what we have done with some data sets. Take a few million pictures and give them to the people of the world and get back annotations.
Right, thanks for the questions, and let's return to them after the sort of hang-around session or after the last presentation. So once again, well, first, give a big hand to Jussi.